For a simple harmonic motion, so we can say a motion in which acceleration is proportional to displacement, and the direction of acceleration is towards the center, or the acceleration increase as the object is moving towards the center. Center, or you can also say a mean position. So we change the statement. Now we are saying, instead of mentioning force and acceleration, we can also use this statement that acceleration is proportional to the displacement, but with a negative sign. If we are able to prove for any motion, if we are able to prove then acceleration and displacement are directly proportional to each other, the negative sign only shows that the object, when it is moving towards the mean position, the acceleration increases. So if a mass attached to a spring, a mass which is attached to a spring, and we want to find whether it is a simple harmonic motion or simple vibratory motion. So we will take a spring. First, it is unstretched spring. We did not attach a load to this. Then I attach a load. So according to Hooke's law states F is equals to Ke or F is equals to Kx. Original length of this spring is L0, and the final length of this spring is L. So if you want to calculate the extension is the final length minus the original length. The difference in the length will give us extension, denoted by x. So when we release this object, like we are holding it at this point. So when the moment we release, what will happen? The spring will apply a restoring force. And what is the direction of the restoring force? The direction of the restoring force will be opposite to the direction of the force which we applied initially. That's why for a spring, we add a load, that is our force, that is equals to K times the extension. But what spring apply, that is minus F, so, or we can also say F is equals to minus Kx, that is a spring by that is a force by the spring. And we have the formula F is equals to ma. In this case, the moment we release this object, the spring will pull it up. So the minimum force which the spring should apply, that should be equal to the weight. So we can say the force which must be applied, it can be more than that, but minimum force will be equal to the weight. So we can write, in place of F, we can write weight, and weight W is equals to mg, or F is, if it was, because if it is in a vertical plane, then W is equals to mg, and the force is equals to weight. But if it was in a horizontal plane, like the same spring was in a horizontal plane and it is vibrating, on an object is lying on the horizontal surface, and you stretch the spring, so spring is vibrating, causing this object to vibrate, undergo a vibratory motion. So in that case, the force will not be equal to the weight. In that case, the force will be equal to F is equals to ma is there, so we can write F is equals to ma in that case. If it was on a vertical plane, then W is equals to mg, I will substitute. So A is equals to, if we need A, so A is equals to minus K divided by M into X. K is a constant, M is a constant. And in a mathematical expression, when we have, like, for example, if two things are directly proportional, if I say x is directly proportional to y, so when I replace this proportionality sign, I replace with equal to and constant. Same thing, now opposite will happen, k and m are constant and we have equal to. So if I want to replace the constant and I want to replace the equal to, so replacing constant and equal to, what we replace with, because if proportionality is replaced by equal to and constant, then constant and equal to will be replaced by proportionality sign. So we can say A is proportional to minus x. So for a mass which is attached to a spring, we get this expression that acceleration proportional to the displacement directed toward the center. So what we can conclude from this, we can say that the mass which is attached to a spring is performing a simple harmonic motion. So the idea, the simple definition, a body which is performing a simple harmonic motion, if it is acted upon by a force, the magnitude of which is proportional to the distance of the body from the fixed position, and the direction is always towards the fixed point or towards the center. So I can also conclude, or I can also say, because we know acceleration and force are directly proportional, so I can also say if a motion force is proportional to displacement but directed towards the fixed point, that is also known as simple harmonic motion. Is it clear, this derivation to show that a mass which is attached to a spring is performing a simple harmonic motion?
Yes, sir.
Then we have a relation here. We can relate a simple harmonic motion with circular motion. How we can relate a simple harmonic motion? So if you remember the formulas for circular motion, what is the formula? The centripetal force, which is F is equals to, this is for circular motion, F is equals to m v square over r, and we know v is equals to r omega. So in place of v, if I substitute r omega, this is r as well, so m, in place of v I substitute r omega, so it will become r omega square over r divided by r. Then it will be m r square omega square over r. Square will cancel with 1r, so the centripetal force, the force which is directed towards the center, is equals to mr omega square. Now we have this formula, F is equals to ma, and we have another formula for a circular motion, F is equals to mr omega square. So if I compare these two equations, force with force, mass with mass, so acceleration in a circular motion, the acceleration is equals to r omega square. Or I can rearrange, just change the position of omega. So I can say omega square r. So acceleration in the circular motion is omega square r. And for a mass attached to a spring, acceleration we already worked out. What is the expression for a mass attached to a spring? It is equals to, negative sign is only showing that direction is toward the mean position, but A is equals to k divided by m into x. So acceleration is equals to k divided by m into x. So this is the equation for simple harmonic motion, and this one is the equation for circular motion. So what I can do, I can compare the two equations. When I compare the two equations, I can say that omega square is equals to k divided by m, or I can say omega is equals to under root k divided by m. So what is the meaning of this? It means like if an object is performing a simple harmonic motion and I want to convert its simple harmonic motion into circular motion. So if I want to convert its simple harmonic motion into circular motion, so what simply I can do, I can use this formula because omega is known as the angular velocity, how many rotations, how many radians are there or revolutions are there per second. So this formula is important, which relate like sometime you have a simple harmonic motion and they ask if the same object is moving in a circular path, what will be the angular frequency or omega, which is under root k divided by m. Is it clear?
Yes, sir.
Same way, we have a pendulum, a pendulum, and what we have a simple pendulum, a mass attached to a string, and we want to identify or find basically first whether it is performing a simple harmonic motion. Length of the pendulum is L. We displace, the angle here is theta. This is also L. The displacement example it is. Maximum displacement will be amplitude or distance at a particular point, that is known as a displacement. So from mean position, say this is x. So here we want to show that it is also performing a simple harmonic motion. So how we can work out this? Weight of this pendulum is acting down. So the component which is responsible for its motion, the vibratory motion as it is moving to and fro. So how we can work out, if I extend this line, so the angle which is formed from the mean position to the string, the displacement position, is same as the angle between the weight, because if I have a transversal intersect of the two parallel lines, the angle forms will be same. So example, if this angle was 30, if there is another parallel line intersects, the other angle will also be 30 degree. So if this angle is theta, here also the angle will be theta. So this is weight, the component of a weight, as we use a trigonometric ratios, the component of the weight which is with an angle, that will be W cos theta, and the component of the weight which is against the angle, that will be W sin theta. Is it clear how W cos theta and sin theta? Because you can see the weight, we have the weight, the angle here is theta, so the one which is with an angle, because this one is a base for us perpendicular, so this the angle where it is forming, that is base for us, so this will be cos theta with an angle, and this will be sin theta. So here the component which is responsible for its motion towards the mean position is W sin theta. So we can say W sin theta is the one which is responsible for its motion towards the mean position, or W sin theta is the resultant force for vibratory motion. So we can say W sine theta is equals to MA. Or I can also say opposite, I can say that we have the resultant force is due to W sine theta, and we know resultant force is given by MA. So I can say MA is equals to W sine theta. Now, the motion is directed towards the mean position. So how we apply a limit here? Because for pendulum, what is the natural motion? If you displace, like if I move the pendulum to position 1, where it will move? It will move towards mean position. If I displace a pendulum to position 2, where it will try to move? So any position, if I try to release the pendulum, it will try to move towards its mean position. That is why this negative sign is showing a constraint here, that the motion is always towards the mean position. Means the tendency of this object is to move towards its mean position. That's why it is written negative here. Now W is equals to mg. So I can write mg is equals to sine theta, because weight is mass into gravity. M will cancel with m. So I get A is equals to minus g sine theta. So if an object attached to a string, a pendulum is there, an object attached to a string vibrating to and fro, we can find its acceleration by using a formula g sine theta. But we want to find whether it is performing a simple harmonic motion. So what I can do, if I simplify this sine theta, here we know this is L, theta is there, and this is a displacement from the mean position. I'm making a triangle with this. This total is L. Maybe it does not appear with the figure, but these two are L, and the displacement from a mean position is X. So according to the right angle triangle, if I apply a sine theta, sine theta is perpendicular. For this triangle, X is a perpendicular, divided by hypotenuse. So this one is a hypotenuse. So L is a hypotenuse. So I can say sine theta is equals to X divided by L. So in place of sine theta, what I can write? I can write X divided by L. So I can say A is equals to minus G. In place of sine theta, I wrote X divided by L. So I can write A is equals to minus G divided by L into X. You can see gravity is constant, length of a pendulum is constant. So when two constants are there, like constant and a proportionality, so when constant and proportionality sign I will replace, when constant and equal to sign I will replace with a proportionality sign. So I can say acceleration is proportional to displacement, and the motion is towards the fixed position. So you can see this statement, that acceleration and displacement are directly proportional and direction of the motion is towards the mean position. So this is a statement for a simple harmonic motion. So this shows that this object is performing a simple harmonic motion. Is it clear that how we show a mass attached to a spring is performing a simple harmonic, a mass attached to a string, a pendulum, is performing a simple harmonic motion? Any doubt?
No, sir.
Then we can also find a relation for finding the between the gravity and length for a pendulum. Like if this pendulum, say one pendulum is there, which is performing a simple harmonic motion, so vibrating to and fro. And another object is there, the same object basically, but instead of a simple harmonic motion, it is moving in a circular path. So if it is moving in a circular path, how we can relate their accelerations? So we know when object attached to a string performing a simple harmonic motion and the similar object is moving in a circular path, acceleration of this object A is equals to minus g over L into x. And for circular motion, as we drive this, that in a circular motion, acceleration is omega square r. So if I relate these two, I can say omega square is equals to g divided by L, or omega is equals to under root g divided by L. Is it clear?
Yes.
So if we want to find a time period of an object performing a simple harmonic for an object moving in a circular path, or for a simple pendulum, so time period of the pendulum, what is the formula? We know time period, time to complete one vibration. In terms of angular velocity, it is angular displacement over time. But if time to complete one vibration or one rotation, that is the angular displacement is 2 pi and the time period is denoted by t. So I can say t is equals to 2 pi divided by omega. And what is omega here for a pendulum? We know omega is under root g divided by L. So in place of omega, I can substitute the value here for omega, which is under root g divided by L. And if I substitute, if I move into numerator, so it will be t is equals to 2 pi under root L divided by g. That is a formula for time period, which you may have studied before, but this is a derivation that how this formula is derived for this is to find the time period of a simple pendulum. Same thing, time period for a mass attached to a string, mass attached to a spring. So if the mass is attached to a spring, the formula for again for time period, we know time period or angular velocity is equals to theta divided by t. Theta is equal, for one complete rotation, theta is 2 pi, the angular displacement, and time period denoted by capital T. So time period we can say 2 pi under root divided by omega. And for mass which is attached to a spring, omega is equals to square root of k divided by m. So we can write, in place of omega, we can write that t is equals to 2 pi under root k divided by m, and if I solve, time period will be 2 pi under root m divided by k. So that is a formula for finding the time period of a mass attached to a spring and performing a simple harmonic motion. So you have to remember these formulas. Basically, if you remember the relation between omega, and for a spring it is k divided by m, and for simple pendulum it is g divided by l. So if you remember this, you can work out these angular velocities, and from that you can find the time period. Otherwise, you can use this formula, direct formula, to find the time period of the objects performing a simple harmonic motion attached to a spring. Now, as we are relating all like simple harmonic motion to a circular motion, so example, you have an object which is attached to a string, and this object is moving in a circular path, and you place a light source at the top, a source of the light at the top. So what you will see, you will observe its shadow underneath. So when you will observe its shadow, what you will see, the shadow of this object which is performing a simple harmonic motion, which is moving in a circular path, is performing a vibratory motion or simple harmonic motion. Why? Because if this highlighted spotlight is representing the position, so what happened when object is here, the shadow will be at this position. So the shadow will move at the bottom, the shadow will vibrate where the object is moving in a circular path. So basically, there is a relation between a circular motion and a simple harmonic motion. Is it clear how its shadow will perform a simple harmonic motion or vibratory motion? Because as the different positions are there, the position of the shadow will be different, vary. But the shadow will return. So the shadow will be at this, here it started with point A, then it will be point B, then point C, then point D, then it will be point E, then point F. So basically the shadow will return and the shadow will vibrate to and fro from its mean position. So the shadow is performing a simple harmonic motion. In short, you can write SHM, where the object was moving in a circular path, so object was having a circular motion. If the radius of this curved path is r and the maximum displacement, the amplitude is x. So moving from point A to point B, So when this object will move from point A to point B, what we will observe, so the maximum displacement is x for the simple harmonic motion. This was a starting point A, and now this is a new position B. This one is R. If it is change angle, so theta, this will be R as well. So now the total length, because the radius is R, but the distance from the mean position, the maximum displacement is x, you can say x naught, and the displacement you can represent it by x. So what I can say, this one is R, so the one which is within angle, that will be R cos theta, and against the angle will be R sine theta. So we can say now the displacement is equals to R cos theta. And what is R actually? R is equals to the maximum displacement, which we can also say the the amplitude, where x naught is the amplitude. So I can say x is equals to x naught cos theta. Is it clear? If I want to find the displacement of a simple harmonic or an object, the shadow is performing a simple harmonic motion. So I can use the formula x is equals to x naught cos theta. And we know the formula omega is equals to theta divided by t. So theta is equals to omega t. So in place of theta, what I can write? I can write omega t. So I can say the displacement of an object which is performing a simple harmonic motion is given by x naught, or the amplitude, cos omega t. So that is the formula to get the displacement. Is it clear till now, this derivation? The displacement of an object which is performing a simple harmonic motion from the mean position, we can say that displacement x is equals to x naught cos omega t. Any doubt?
No.
Now, what about the velocity? So you have this formula x is equals to x naught is the amplitude cos omega t. If I differentiate or take a derivative, maybe those who are taking mathematics, they're studying the calculus. So if I take a derivative, x naught is the amplitude which is constant. So we remove this constant out, and that is cos omega t. So if I take a derivative, that means if I find the rate of change of displacement, I will get velocity. So this will be x naught. What is the derivative of cos omega t?
Negative sine omega t.
So, but it will be omega minus omega sine omega t, because we are taking a derivative with respect to t. So omega, first a chain rule will apply. We'll take out omega. I'm not going in mathematics now, but when, like example, if I'm taking a derivative of cos theta, I will write the derivatives for all. What is the derivative? If you derive or take a derivative for cos theta, it will be minus sine
Negative
theta.
sine theta.
Sine theta. Yeah, negative sine theta. And if I take a derivative of sine theta,
Cosine theta.
so it will be cos theta. So that is why, but here we are taking a derivative. What we are taking? We are taking d by dt of cos omega t. So omega will come out, and then we'll take a derivative of cos t, which will come out sine. First we will assumption is there for this as one function, omega will come out. So the derivative will be minus omega sine omega t. So I can say v is equals to minus x naught omega sine omega t. So this is a formula to calculate the velocity. If I need acceleration, I will take a derivative again. So when I take a derivative again, so I will take a derivative. I'm writing the final result because less than a minute left. In the second session, I will explain what is and how we will get the result. So if I take a derivative of the velocity will be acceleration. It will be minus, it will remain here. X naught and omega are constant. So when I take a derivative of sine omega t, derivative of sine theta is cos theta. So it will be omega cos omega t. And when we solve this equation, so we'll get acceleration to be, so the acceleration will be minus x naught omega square cos omega t. This is a formula for acceleration of an object which is performing a simple harmonic motion. Is it clear?
Yes.
Less than a minute left, so I will continue in the next session this part and share a link within a minute.